J'arrête l'enregistrement. Ah oui, d'accord. C'est les mêmes délires. On n'a pas vu les choses. Okay, I can maybe restart. So it's for this second lecture in this afternoon. So afternoon is for us here. It's my pleasure to introduce Raquel Perales from University of Mexico in Oaxaca, and she speaks about recent intrinsic flat convergence theorems. And it is a sequel, well, it is part related to the lectures by Christina last week. So please, Raquel.
Okay, so thank you for the invitation and let us start. Okay, so first, let me. So I'm going to give just one slide of motivation of why we want to do this type of things. So there are some theorems that involve a scalar curvature. So for example, the first one in which we have a torus and it has non-negative scalar curvature, and then we know that it has to be a flat torus. And another result is the following. So this result is part of the positive mass theorem, but I'm just giving you part of it. So we start with a complete and asymptotically flat Riemannian manifold. This manifold can have a dimension higher than 3, but I'm just writing here 3, with a non-negative scalar curvature and a diam mass equal to 0. So if these conditions hold, then the manifold has to be actually the Euclidean space. So the flat Euclidean space. And then one wonders what happens if we try to relax these conditions. So for example, in this theorem, maybe we allow the scalar curvature to be negative, but very close to 0. And in this second theorem, maybe we allow the ADM mass to be positive and very, very close to 0. So what would happen if we take a sequence of manifolds satisfying these conditions? Would they converge to a flat torus or to Euclidean space? And the thing that we have seen is that if we use the Gromov-Hausdorff distance, then we can easily obtain counterexamples to converging to a flat torus or converging to a Euclidean space. And then we try to do something else. And something else means, okay, we will try to use intrinsic flat distance. And okay, so I think this year there was a result by Lee, Neighbor, and Neumayer, in which they proposed another type of distance to deal with scalar curvature bounds. And okay, so why do we want to use intrinsic flat distance? Well, let's look at this example. In this example, I have spheres, and one is the, so this is a sequence of manifolds. So this is M1, and it's this gray manifold, and then M2, and M3. So they start having more spikes, which actually are thinner. So if I continue in this way, this sequence won't have a Gromov-Hausdorff limit because we are creating too many spikes, so the limit could not be compact. And hence won't have a C0 limit, but it has an intrinsic flat limit. And this intrinsic flat limit is this sphere that we see here inside of our manifolds. Okay, so this is the motivation. And now let me tell you which convergence theorems I'm talking about and the applications. Okay, so these are the convergence theorems. These were with Allen and Sormani, and a second one with Allen. So let us read this theorem. So what we are doing here is we are fixing a manifold M, and this manifold has to be oriented in order to apply intrinsic flat convergence or flat convergence. Okay, so this manifold is oriented, and we will ask it to be compact with or without boundary. And then we fix a metric tensor G0, and actually we want at the end, so in this theorem, we want to converge to this manifold M with this Riemannian tensor G0. Okay, and then we have a sequence of other Riemannian tensors, Gj, which are going to be only continuous. And then we require the following conditions to our Riemannian tensors. So we want distances measured with G0 to be less or equal than distances measured with respect to Gj. A diameter bound, and the volume convergence to the volume of M0. Okay, so if we have these conditions and we don't have boundary, then the whole manifold immediately converges this sequence of manifolds immediately converges to the fixed manifold that we wanted to converge. Okay. So this is very nice because, well, first let me tell you, there are compactness theorem for intrinsic flat distance, but you don't know what the limit is. You only know that it's an integer rectifiable space. So it's good to have where do you want to converge. So this is the novelty of the theorem. And well, the second part is that if you have boundary, then you also converge to MG0 if you ask another conditions. And well, you have to ask conditions on the boundaries of the manifold because now you have boundaries. So one of these conditions is that the areas are bounded, uniformly bounded, and that your manifold is geodesically convex, has a geodesically convex interior. And by that, I just mean that given 2 points in the interior, you can join them by a geodesic that remains in the interior. And then there are other 2 more possibilities in which you also have convergence that involves some convergence of the Riemannian tensors, but just, well, this is okay. Okay, this one, for example, is just at the level of the boundaries. Okay, so I'm not going to talk about these 2 last results. I'm just going to focus in these first 2, when you don't have boundary or when your boundary is geodesically convex with respect to the fixed Riemannian metric to which you want to converge. Okay, so then what can we do with these theorems? With these theorems, we can prove the following. So some result about the stability of the positive mass theorem, which says we can come up with a class of manifolds. And within this class, if I take a sequence of manifolds, Mj, and I require that the ADM mass converges to 0, then we will have intrinsic flat convergence to where one expects. So this BR is an Euclidean ball. And here, this is also an Euclidean ball. So let me tell you a little bit about these 2 results. So this second one, you can actually think about it as a pointed convergence theorem, because here I'm saying for each r greater than 0, then your ball around the point Pj of radius r is going to converge. So this is contained in your manifold Mj, is going to converge to Euclidean space of the right dimension. Okay, and here we are choosing any sequence of points in certain region, and you have to choose them in certain region because when you use intrinsic flat convergence, there are many things collapsing. So if you choose your points, for example, in my motivation photograph, so here, if you take your points here in the spikes, well, and since we know that this sequence converges to this red sphere, so then these points disappear in the limit, okay? So we have to choose carefully those points. Well, more or less. Okay, so this is one of the applications, and the other application has to do with the rigidity of the torus. So we also came up with some class of tori, and then we required the scalar curvature to be converging to 0. So this is going to be negative and converges to 0. And then we have two things. Either the volume of the whole manifold goes to 0, so that then we have a sequence that collapses completely, or there is a subsequence of mi's converging in intrinsic flat to what we expect, so a flat torus. And the limits of the flat torus converge to the volume of the limit flat torus. So here it is. And this can be done in any dimension. This tori, well, dimension higher or equal to 3. But if we are in dimension 3, Christina talked about some condition called min A, and it's about bounding the volume of minimal surfaces in your manifold. So if you also impose this condition of the min A bounded by some positive number, then we actually cannot have this collapsing thing. So you only get sequences, well, sequences that have subsequences that converge. Okay, so these are the theorems and I'll try to explain how to prove all of this or some of this. If you have any questions, please stop me. Okay, and first let me try to say a little bit more about these classes of spaces. Oh, so let's talk about asymptotically flat manifolds. And here what we have is the following. So I actually don't want to go into the details. I just want to give you just a rough idea about which class is this one. And then everything started with a paper by Wang and Li in 2014, in which they define a class. And this class, what they proved was stability of the positive mass theorem, but using the flat distance instead of the intrinsic flat distance. So let's read what this says. So we have manifolds of dimension greater or equal than 3, and they are actually going to be graphs over a function. So you have x and then fi of x, okay? And so this function fi is going to be defined, well, in Rn minus some ball. And actually this ball can be actually the empty set, in which case we say that this manifold is entire, or it can have a minimal boundary. So this is the example. This here, we will have a minimal boundary, and this is the graph over this function f. Okay, and we require certain conditions on our functions. So we want that the inverse, well, that the level sets are strictly mean convex and outward minimizing. And I won't say much about this, but actually, okay, yeah, the thing that I wanted to say is that asking strictly mean convex is not that much, because with this information from the first 4 lines, we actually know, or actually Huang and Gu knew, that the level sets are quickly mean convex. So you just go from weakly to strictly mean convex. So it's not too much. And then in dimension 3 and 4, the manifolds behave in a different way. And so they have to require extra conditions that I'm not going to read. But anyway, for this class of manifolds, if you take a sequence whose ADM mass converges to 0, then you have to vertically translate your manifolds a little bit. And then once that you translate your manifolds, you choose a ball because you want to calculate a flat distance within a ball. And in this ball, you have then intrinsic flat convergence to the 2Rn cross 0. Okay, so the Euclidean space of the right dimension. And okay, so let me explain you why all these conditions are super nice. So these conditions on the functions are very nice because they allow you to calculate something. So they allow you to say that that fixing this, the 0 level, in this 0 level, so from here to the bottom, the level sets are going to have very small volume. And then starting from 0 to the top, you know how high is your graph. Okay, so if you want to calculate flat distance for those, you know, having a small volume here and having U is a fixed ball of certain radius, so you can calculate some volume here using these two properties. And in this part, knowing that the height is actually bounded by something that actually depends on the mass, and that you are in this fixed ball of fixed radius, also allows you to calculate some volume, and then it tells you that the flat distance goes to 0, because everything you did, you calculated in terms of the mass, the ADM mass, and this ADM mass is going to 0. Okay, so this was the class. And then Christina Sormani came into the picture, and she said, okay, what about if we try to prove an intrinsic flat convergence result instead of a flat distance result? And first of all, flat distance does not imply intrinsic flat distance, so they have to put more conditions to this class. So let me pass to that slide, and I'm going to skip this one, which were details about the other slide and other details. Okay, so here Sormani comes into the picture, and she says, okay, what about if we work with the same manifolds that Huang and Lee used, but we are going to require more conditions. And one condition is that if you have an U, so this U is the one that has the minimal boundary, that it has to be within some ball of fixed radius. So here we have R0 divided over 2. And then in the exterior region, what you want is that the gradient of your function, well, the norm of the gradient of your function is bounded by some constant gamma. So actually you are asking that the exterior region, you have some type of, this will give you that F is Lipschitz. It's gamma Lipschitz, or with some constant that depends on gamma. Okay, and the other thing that you want to do, or that we want to require, is the following. So if we look at this picture, we are fixing radius R0, and what I have is the manifold, and I intersect it with a cylinder. And this cylinder has radius R0. So this is what I'm doing. The manifold intersected with the cylinder. And then I get this sigma, so this surface, or boundary of this region. And we want to measure how deep we can go from this region to this part in the bottom. So this is the depth. So it's a supremum of the distances of points that lie in this region to the boundary sigma R0. Okay, so we want to measure that. Okay, and once that they came up with this class, well, they tried to prove the theorem that I told you some slides some slides below. Well, I don't know how to say this. Okay, but anyway, so they try to prove the theorem that I told you, which says, okay, so now we can read it again. It says that within this class, if the ADM mass converges to 0, then you have, and now I can tell you this. So these omega j's are the regions of your manifold intersected with this cylinder of radius r. So these regions converge to a ball of radius r, or you can also look at balls in your manifolds, and these are metric balls, and they converge to the Euclidean ball. And here you have to choose your points, Pj, in these boundaries that I told you of the sigma j r0. So they are actually in this part. Here is where you can choose your points, because what is going on, I mean, if you read again these conditions, we actually don't know much about what is happening inside the ball BR0/2. So that's a region that you don't know much. And in the exterior, you have a lot of conditions, like this condition on the norm of the gradient of F, okay? So, and that's why we have to choose the points in this part. We can choose them in the more exterior region, but if you start choosing points here, this is going to be nice, and it will give you convergence. And okay, let's read a little bit about the sketch of the proof. And the sketch of the proof is as follows. So first, using the existence of this H0f. So this H0f was the height that was telling you that below this height, the level sets have small volume, and above this height, well, your graph or your function cannot grow that much because it's controlled by the mass of your manifolds, okay? So we have these two quantities that are very nice, and then you can calculate volume, diameter, and area estimates of your manifolds. And if the manifolds are entire, that's when the U's are empty, then you can use right away my theorem with Allen. And let me remind you what was my theorem with Allen. So you have manifolds that are compact, oriented, smooth manifolds. Well, sorry, I just repeated manifolds. But anyway, you wanted the Riemannian tensors to satisfy this inequality. And we actually have it right away because your manifolds that we are creating are graphs over, I mean, they are graphs, so they come from a function. So actually your Riemannian tensor is going to be just the Euclidean tensor plus df tensor df. And so this inequality is going to be satisfied right away. And the diameter and the volume and the area, well, and the area bound, this just comes by the existence of these two nice quantities, the height and that F doesn't grow that much, okay? So then you can right away apply the theorem and get convergence to the Euclidean ball. And that's how you prove this part. Now, how do we prove the second part? Well, the second part is a little bit more tricky because I told you about these points. And actually here, what one has to use is one has to prove that in the exterior region, in some annulus, we have a Gromov-Hausdorff convergence. So these points that I'm going to choose, these points Pj, are actually going to converge in Gromov-Hausdorff sense. And because they converge in Gromov-Hausdorff sense, they are not going to disappear. I mean, if I take a sequence, then a subsequence will converge. So we are not in the scenario in which the point disappears in the limit. But then there is Gromov-Hausdorff convergence and there is intrinsic flat convergence. And you want to prove an intrinsic flat convergence result. So what you have to make sure is that there is some compatibility of this convergence. And this is something that actually Wang Li and this is something that Wang Li and myself did in this paper in 2021. So we studied the compatibility of Gromov-Hausdorff and intrinsic flat convergence of points in some regions. Well, I don't know. So let me go to the other part of my talk, but if you have questions, you can interrupt me. Okay, so now how do we prove the new recent convergence theorems? Well, this, if you were last week attending Christina Sormani's talks, you probably know this. So this is going to be some refreshing of intrinsic flat theory. So intrinsic flat theory goes as follows. You start with a complete metric space, and then you look at this set. And in this set is actually m+1 tuples of Lipschitz functions. So here we have m Lipschitz functions, and then the first coordinate is going to be also bounded. Okay, so now that we have this space, a current, an m-dimensional current that corresponds to this m, is a multilinear function. So this multilinear function, we write it as t, so it goes from this space to the real numbers, and it satisfies certain conditions that I'm going to skip because I don't want to, well, I will say them in the next slide. But let's look at the examples because the examples explain everything. What you have, so first example is that you can have a function, an L1 function in Rm. And what we are going to do is we are going to create this current that has double brackets. So this current double brackets is going to eat a bounded function, bounded Lipschitz function, and then these pi1 up to pi m Lipschitz functions. And what you have to do is integrate your theta function, which is actually called weight, and then multiply it by f. And then this pi, well, this pi is a function that goes from Rm to Rm. So actually you can take the derivative, which exists almost everywhere, and then you can take the determinant. So you multiply all these things. You multiply all these things and integrate, and that's your current. And then the next step is push forward. And push forward means you have a Lipschitz function. So now we are going to leave Euclidean space, and this set is a metric space. So we will have a current in a metric space. So, and it's denoted this way. So push forward of our theta current. And what it does is the following. So here you have theta evaluated at your point x. Maybe I need a phi here or a phi here. Okay, but so you have the weight function. No, this is defined. Okay, so you have your weight function and then you multiply by f. And then what you are going to do is compose your pi with phi, and again, take the derivative and calculate the determinant. Yeah, so probably I'm missing here a phi. Okay, but anyway, so these are the main examples of our currents. And the properties that I skip of this functional are the following three, which the only thing that is really necessary for what I'm going to say next is that there exists a finite Perales measure that satisfies the following property. So you can bound your current, well, the absolute value of your current in this way. So what is going on is these pi i's come out of the integral, and then you only have the integral of f multiplied by some measure. So if we go back to the example, what is happening here, I mean, you are taking like this determinant to the outside, and then you get f, and actually your measure is going to be theta in the Lebesgue measure. Okay, so that is what is happening here. And some other definitions, well, the push forward that I told you, which means just compose your entries with the function phi. And the boundary just means put a 1 in the first column, which is a Lipschitz function that is bounded. And then there is this mass measure, which is the smallest Perel measure that satisfies this inequality one. And then the mass of your current is just simply take the mass measure and evaluate it in all your metric space. And then here we have set of T are points whose lower density with respect to this mass measure is positive. Anyway, so maybe you don't need this because we are actually using this for manifolds. And then an m-dimensional integer rectifiable current is simply adding up all these building blocks that I told you about. Okay, so it's a current that you can write as a sum of these building blocks. And then these building blocks, well, we know that these phi i's have to be Lipschitz functions, and actually one can make them by Lipschitz. And then for convenience, we require that the images are pairwise disjoint, but you don't need to have them. And they are called integer because these weight functions that I was telling you about, they have to be integer. And that's why I put them outside of the integral, because you can take them out if they are integer. And then if you put the following requirement, that the boundary is also a current, because I didn't tell you, but the boundary might not be a current. So if the boundary is also a current, then this current T that is written this way, it's called integral rectifiable current. Okay. And the main examples are the following. So these are actually the ones that we studied. You can have a submanifold, and then your submanifold has charts. So actually you can write a current in this way, where one uses the weights to be equal to 1, as I put them here. So I'm just choosing the function 1. And then another one that is more interesting is that you can choose, for example, in this example, it's anyway. So I divided my manifold, which has a boundary, into regions, the annular region and the smaller ball. And in the smaller ball, I put multiplicity 2, so the weight equals 2. And then in the annular region, I put weight equal to 1. And then this is a current, or an integer rectifiable current, or an integral rectifiable current. And it has two boundary components. One that comes from this one, the outer circle, and then an inner circle because the multiplicities don't match. Okay, so then you know what it is, and I can talk about the distance that we use. So the distance that we use is first, one has to define the flat distance. And the flat distance just means if you have one current, which is in red, and another current, which is in blue, and look at here at my picture, and remember they have to be oriented. So these arrows represent the orientation. And then what you have to do is take the infimum of the mass of one current that is the same dimension as my original currents. And it's this one in green and this part in green. And then plus the mass of this current that has one dimension higher. So this is the picture. And so these U's and these B's have to satisfy this condition, which is like a cobordism condition. But it's also like a Stokes theorem, okay? So you just want to fill in your T2 and T1 by something that has higher dimension, but maybe you created some boundary, and that's why you need this U, okay? Good. And then intrinsic flat convergence is to have this metric space, and then you have a current here. And if you want to calculate the distance between them, you take isometric embeddings and you to some bigger space set. And in there, you calculate the flat distance, which is the one that I just explained in the previous slide. And again, as in the Gromov-Hausdorff case, you have to caution out. I mean, it's not a distance right away. So this distance is going to be 0 if and only if there is an isometry between your metric spaces that send one current to the other one. And then the main example, which is actually the one that we use, is that if we have a Riemannian manifold, well, we take M, we take the distance that comes from the Riemannian tensor, and then we have this current M, and this is an integral current space. So you can calculate the intrinsic flat distance between these spaces. Okay, so this is the mini course of Christina in like 15 minutes. And just to sum up, if you want to calculate intrinsic flat or Gromov-Hausdorff distance between two manifolds, so an M1 and an M0, well, what you have to do is maybe construct a bigger space, Z1, in which you can put those manifolds there, so they isometrically embed. And then there you calculate either the Hausdorff distance or the flat distance. And I mean, this is my picture. So here I have M and M, which are actually the same, well, more or less. Yeah, so here's one, here's the other one, and the space that one created looks more or less like a cylinder with top U1. Okay, and once that you embed this, if you have a sequence, because we want to consider a sequence of manifolds, and we want to show that it converges to some fixed M0, well, what you have to do is maybe create one space for each pair, like MJ and M0, embed there, take the Hausdorff or the flat distance inside, and hopefully, if your embeddings were chosen correctly, then the limit of these distances is going to go to 0, and hence the intrinsic flat distance is going to go to 0. Good. And now let me tell you how to prove some of the convergence terms. So I told you I'll just focus in the case in which there is no boundary, or where the manifold, the fixed manifold, has convex interior. Okay, so what we want to do is create this space, this big space set, in which we can embed our manifold MJ and our manifold M0. And for that, well, let's read this theorem. So basically, the first two lines, we already know them. So we have an oriented compact manifold, M, and we have Riemannian tensors on our manifold. The first one has to be, actually in this theorem, G and GJ, all of them can be just continuous Riemannian metrics. Okay, so we have these Riemannian metrics, and we require that distances with respect to G0 are smaller than distances with respect to GJ. And so, because distances with respect to G0 are smaller than distances with respect to the GJ, notice that we will have something that looks like what I have in blue, but reversed. I mean, we have DJ0 less or equal than DJ. And so this slide, I mean, this part in blue, I'm saying let's have the reversed inequality, but maybe with some error, and just in one particular set. So in a set W that is contained in M, okay? And let's make this set W to have big volume. And I'm saying big volume because here we measure the volume of the complement, and we want this Bj actually to go to 0, okay? And then what we are going to do is construct this space in which we are going to embed our manifold M0 and our manifold Mj. And this looks like a cylinder. So let me just, so this part, Mj times 0Hj, so it's the cylinder that has as base Mj, and the height is going to be Hj. And then what we are going to do is that in the top, we add our manifold Mj, and in the bottom, we add our manifold M0. So actually, we are identifying M0 to the bottom, and then Mj, we don't identify the whole Mj. We just identify the points that are contained in this W, which has big volume. Okay, and then we have to put some metric in this space that we just created. So putting the appropriate metric, what we can do is prove that the flat distance of M0 and Mj in this space is going to be bounded in this way. Okay, and now let me tell you. So I told you, we wanted this, we would like this Bj to go to 0. So then we will have this going to 0. And then we will want this Aj also to go to 0. And so this part is going to go to 0. And also this part is going to go to 0 because we will have volumes converging, and then we will have, if we have boundary, we also have that the areas are going to be bounded. So we will get in the limit intrinsic flat convergence. Okay, so now let me give you some ideas about why or how this space is constructed, or why this works. So first of all, let's start with the trivial example. So the trivial example is that I have the same manifold, okay? So I have the same manifold, and then what the space that I construct is just the cylinder over my manifold M. So this is actually the picture. So M0 and MH, and they are the same manifold. And I mean, since they are the same manifold, actually their flat distance is the same, but this is just to show you how this works. Okay, so then we want to come up from the definition, we want to come up with this space that has higher dimension, and we take the boundary. So this space that has higher dimension is the whole set. And if we take the boundary, what we are going to get is this, I mean, it's this two-dimensional cylinder, right? The bottom and the one to the sides. So we will get these two parts when we calculate the boundary of this cylinder, but we also get this boundary that comes from the sides. Okay, and so it satisfies the condition that we want in order to be able to calculate this flat distance. Okay, and so the flat distance says, well, take the volume now of this yellow region, so of my cylinder, and then take the volume of this other part. And well, it's easy to calculate the volume in this case. It's just the height times the volume of M, and then the height times the volume of the boundary. So this is what we get. Okay, so that's trivial example. And our next example is when we have, let's say we have the same manifold, but then in H, we put a Riemannian tensor such that the distances there are smaller. So maybe we divide by 1/2 or something. So we have here NH, and here we have N0. And then we can play the same game. So we construct this kind of truncated, truncated figure to calculate the flat distance. And we can do it that way. But actually what we are going to do is we have a one Lipschitz map that takes all these cylinder into this truncated cylinder. And so we are actually not going to worry about working with volumes in this truncated cylinder, and everything we can just, we just want an inequality. Okay, so then we just use the inequality that comes from this cylinder. And that's it. So we don't have to worry that much. Okay, so that's my second example. And my third example is actually what we do in the theorem. So in the theorem, what we have is an M0 that has short distances, and then we have an Mj that has bigger distances. Okay, and then we have a region W that has distances very close to M0. And here my picture is not really nice, I'm sorry, but I'm saying that this M0 has similar distances to this part in red, okay? And remember that we glue Mj to this part, but actually we just identified points in Wj. So because we only identified points in Wj, that's why we have this other thing and this other thing coming here. And we can play the same game as when we had a cylinder and calculate the flat distance of this type of picture. And what we get is, well, this part that looks like what we have in the cylinder. So the height times the volume of the manifold plus the height times the volume of the boundaries. But then we get this extra part because we have these things coming out from our metric space set, okay? And if you want a real example, this is the real example. M0 is the manifold in pink in the inside, and MJ is this manifold that consists of the blue part and the yellow part. And so the blue part is our set W, the one that has distances that are close to M0. And then the yellow part are points in which the distance does not have very well control. Okay, so that's how we constructed this space. And then, I mean, the only thing that was missing in this theorem is that here I say, okay, you have a W, you start with a W. So in this next slide, I tell you how to construct this set W that has big volume and that has distances very close to the distance of your manifold with respect to the Riemannian tensor G0. Oof. Okay, I hope this doesn't move again. Okay, so you can construct this W once that you have this condition. So this condition is telling you that if you have your Riemannian tensors as before and a volume bound, and your distances converge to the distance, I mean the distance with respect to J converges with respect to the distance, converges to the distance with respect to G0, if you have this almost everywhere convergence, then you can construct these W's that satisfy the conditions that we want. Here I just put more details, so don't worry. I mean, this is some small thing that is going to go to 0. And this thing is also some small thing that is going to go to 0, because we will have that the volumes of the MJs converge to the volume of M0. And here, because I have the volume of a fixed manifold, and I'm going to let this kappa to go to 0. So these are precisely the things that I really wanted to have. Okay, and now let's see what the next slide says. Oh, the next slide has many things, but let's don't worry about this. So, okay, so there are many lambdas and many kappas and many things. Don't pay attention. I mean, the main idea is the following. Suppose that one has this pointwise almost everywhere convergence. Okay, so, but here we have this pointwise almost everywhere convergence in the spaces M times M. Okay, so then we can use Egorov's theorem. And Egorov's theorem is going to say that given an epsilon, you have some region in your manifold M0 times M0 that has a small volume. And this, sorry, that has very big volume. So this is quantified in this way. So 1 minus epsilon volume square of M0. So this has big volume. And in this region S epsilon, we will have actually convergence of DJ, of our metrics DJ to D0. Okay, so, and it's quantified in this way, our convergence. And now that we have this set, as epsilon, what we actually want is a set in our manifold M. So what we are going to do is take the projection of this S epsilon to M and look at what you get. So we have here our projections to our manifold M. So we fix a point Q and then we see what is in our manifold M. And then because this volume is actually big, our projections are also going to have big volume, or for some points. For most of the points, we will have also big volume. And thus, we define this W to be equal to the points P such that its projection has big volume. And this volume is quantified in certain way. So here's where the kappa enters. And because we require this condition, we can prove that the volume of this set W is actually big. And I mean, it's big because remember that, well, this kappa minus 1 divided by kappa is going to be close to 1. And we are going to let kappa to go to infinity. Okay, so then these have big volume, and those, the complements have small volume. We can quantify it in the way that was written in the previous slide. And now we only need the condition of the distances. So we wanted this set W to have a distance very close to the distance of the manifold M0. And now what we have to do is just some triangle inequality to say that our projections actually intersect, and then do some triangle inequality as I told you. Okay, and so we get this, well, this estimate. This one comes from, I mean, this 2 delta lambda kappa jota comes from this because we used Egorov. And then this lambda comes because we have non-empty intersection between our projections. Okay, and that's how we got this W. And just to recap, how do the proof of the theorems go? Well, if your manifold has no boundary, or if the boundary exists but has totally convex interior, here I said recall, because actually this was proven. So this convergence of these distances almost everywhere was proven by Allen and Sormani. So we already had that thing. And then second step, prove the existence of these sets W's that have the required distance conditions and volume conditions. And because we have now this W set, we can construct these spaces in which we can isometrically embed our manifolds. And I told you that the flat distance was, I mean, we had this flat estimate that depended on the height and depended on the volume of our manifolds. And so we get this convergence taking out the lim sup when j goes to infinity, and then the limit of this kappa to infinity and lambda to 0. Well, I mean, this part was just a little bit technical, but that's it. And I think I'm going to, I mean, for the people that were interested in what happens if you have boundaries, we actually had to take a double of our manifold. So actually what we did is, so you have your manifold and then you put an egg. So here we have an egg. And then in the other side, we have our manifold. So we glue our two manifolds by attaching an egg from one boundary to the other boundary. And then we had to do, then these new manifolds, we put some Riemannian metrics on them. And you have to play a game about this MJ delta being close to MJ. And then the MJ deltas, now that they don't have boundary, you want to use the theorems that we already proved for this new sequence. And then you have to do some triangle inequality game to show convergence of the manifolds with boundary. And that's it.
Thank you very much, Raquel. Thanks. So are there any questions? We have time for questions.
May I ask a question? Sorry.
Yes.
So do you, so once you know about, so that something converges in this intrinsic flat sense to somebody, you know, to something, you know, what can you deduce from it?
I mean, these spaces are countably rectifiable. So you already know that. And then what you know is that the filling volume behaves well. So that one is continuous with respect to the distance, unlike the mass.
Mm-hmm.
Yeah, the volumes are just lower
The filling
semi-continuous.
volume.
And then you have convergence of slices. That is basically, well, yeah, convergence of slices.
Thanks.
Yep.
More questions? Felix? Okay. Well, if there is no more questions, thank you very much again for this nice talk, Raquel.
Thank you.
Hope we'll see each other sometime, somewhere.
Yes.
Thank you.
Thank you very
Thank
much.
you, Raquel. Beautiful talk.
Thank you.